Industrial plants are filled with explosive gases and volatile chemicals. All it takes is one tiny spark from a rogue electrical wire, and you have a disaster. So how do we plug electrical sensors into these highly explosive zones safely? We use an intrinsically safe barrier. Today we are going to crack one open, look at the circuit board, and explain exactly how galvanic isolation keeps explosions from happening. This is the Eaton MTL5544D. Before we tear it apart, let's look at the outside. The entire purpose of this device is to sit right on the border between the safe world and the explosive world. Notice the color coding. The gray connectors on the top right go to your safe area like your control room and power supply. But look at this blue connector on the left. In the automation world, blue means intrinsic safety. That is the side that wires directly into the hazardous field. Now let's look at the guts. This is where the magic of galvanic isolation happens. Older barriers use simple fuses and diodes to dump dangerous voltage into the ground. But look closely at the middle of this circuit board. There is a literal physical gap. No copper traces cross this line. If a massive 240-volt power surge hits the safe side of this board, it physically cannot cross over to the explosive side because the road is missing. So how does power and data cross an empty space through these transformers? The larger ones turn the DC power into a magnetic field, beam it across the gap and turn it back into usable power for your sensor. The smaller ones do the exact same thing in reverse to bring the 4 to 20 milliamp measurement data back. There are 0 wires touching between the two zones. To really understand how this works in a live plant, let's look at the full system layout. We have 3 zones: the field where the transmitter lives, the cabinet where our MTL barrier sits, and the control room housing our PLC. We supply the main 24-volt power directly into the barrier. The barrier then acts with an active input and an active output. First, it actively supplies the necessary base voltage out to the field. But here is the key for the measurement: the sensor, or your field calibrator, provides the active power signal back. As the transmitter measures pressure or flow, it actively drives that 4 to 20 milliamp power signal back down the line to the barrier. The barrier takes that exact fluctuating current, jumps it magnetically across the isolation gap we just saw, and actively sources that same 4 to 20 milliamp signal straight into the PLC in the control room. As the transmitter's value changes in the field, it drives the change in the current signal all the way down the line, keeping everything perfectly isolated and safe. And that is galvanic isolation in a nutshell. If you found this teardown helpful, hit that like button and subscribe for more deep dives into industrial automation and instrumentation. See you in the next one.